Good afternoon. I brought with me a couple colleagues, Stephen Chin and Robert Savage and myself, and we're going to be talking to you about Raspberry Pi development with Java 8. Now, who here has just heard of the Raspberry Pi, that small computer board? Who's heard of it? Okay, most of you have heard of it. Okay, so who has actually purchased one? Okay, all right. Now, who has actually done any development on one? Gotcha. Maybe half of those that have purchased one. So what our mission in life today is to teach you, make it approachable so that you can actually go home and develop on your Raspberry Pi. So again, my name is James Weaver. I'm going to give you some introductory stuff. I'm going to do the easy stuff. And then you're in for a special treat. At the end of my short introduction of concepts, the last thing I'm going to introduce or show you is this client-server application that talks to the Pi, and it's written in JavaFX. And we're lucky enough to be joined by 4 college students that won a programming contest, and they did a project in JavaFX. So they're going to spend just a couple of minutes telling you about that, and I'm sure that you'll want to greet them warmly when they come up and really encourage them. And then my colleague Robert Savage, who was the person that created Pi4J of Savage Automation, is going to explain to you what Pi4J is. And I won't steal his thunder by even hinting at what it is. And he's going to give you some basic and then show some cool demos. And then Stephen Chin is going to reach into his bag of tricks along with a colleague of his and ours, Michelle Hoffer, who's going to show you some really cool stuff. So you're in for...
Mainly I just get to show you guys some toys.
Right. So yeah, he's one on my team, and yeah, he gets to play with fun toys. So we've got a packed 3 hours. Somewhere in there, we're going to give you a 10-minute break. Robert is going to excuse you for a 10-minute break sometime during the middle of his presentation when he thinks it's appropriate. So, name's James Weaver. I'm a Java Technology Ambassador for Oracle. If you want to get a hold of me, it's james.weaver@oracle.com, and my Twitter handle is JavaFXpert. The presentation, I should tell you, my part of the presentation is very loosely based on parts of this massive open online course that Oracle has created for developing Raspberry Pi with Java ME, Java Mobile Edition. And so it's a 5-week course, online course, and in about 35 minutes I'm going to take you through some of the highlights of that course, enough to where you've been exposed to a lot of the different concepts so you can hit the ground running. Also, I would encourage you to go look at that course. It's free and freely available. It's got lots of video in it and lots of resources. It's really well done. I guess I shouldn't stress that point too much since I was one of the ones that created it, but I think it's well done. And then there's a tweet. If you look at your Twitter history, if you look at my latest tweet, JavaFXpert, you'll see a tweet for the link where that course is. So you could even access the course now if you wanted to and begin looking at some of the slides or whatever. So what's a Raspberry Pi? You all know what a Raspberry Pi is, but just for maybe a few of you that don't, it's a very small, cheap computer. It was built in the UK to help educate students, bring kids up to speed in computer programming and computer hardware. It's a microcomputer without peripherals. It's got lots of ports, like this RCA video port for a composite output, or SD card, or LAN, Ethernet port, HDMI output. It's got 512 megabytes of RAM, and it's 700 megahertz processor. Here's a picture of it, and showing some of the peripherals or jacks. So you can have 2 USB ports for a keyboard and a mouse, Ethernet, as I said. It's powered by a micro USB, and then you can insert an SD card in it. Now, up in the upper left-hand corner is what makes a really good embedded platform. That's a 26-pin general purpose input-output header, and you can hook up different things to that, different peripherals to that, like devices, switches, actuators, and other peripherals. And I'm going to show you. A lot of the talk today is going to be about what are some of the protocols, how do I hook things up to that 26-pin header. So first of all, I'd like to talk to you about what Java ME is. So you know what Java SE is, and it's got, it's got an API that has lots of different things that you don't really need in the embedded space. You don't typically need JDBC, for example, or AWT or Swing or some of the other things. So that's why it's showing that ME is part of it is a subset of Java SE. But also you notice that there are some things in ME that aren't in SE. For example, device I/O and other things that I'll be showing you here. And ME is really great for smaller devices, like your remote sensors that could be 1 inch square, or the Raspberry Pi, or meters and things like that. So embedded devices, all the things that we're talking about now in the Internet of Things, Java ME fits really well in that space, and developing on the Raspberry Pi helps you prototype and kind of learn to code for the Internet of Things when you're dealing with Java. So the Java ME architecture on the Raspberry Pi is at the lowest level. You've got the device, and on the device is an operating system. For the Raspberry Pi, it runs Linux. As a matter of fact, there's a special distribution of Linux called Raspbian, which is based upon Debian. And the Raspberry Pi has an ARM chip. And above that, we have a basic set of libraries and a virtual machine. And that's called CLDC, Connection Limited Device. And then above that, we have a set of APIs called MEEP. It's ME, I can't remember what MEEP stands for. Look it up. So anyway, we just call it MEEP, and it supports a range of devices. And there's some optional things on that let you talk to Bluetooth and other things, do device I/O and that kind of thing. So in the tutorial, in the MOOC, it talks about how to set up your installation. And so all you need is Java SE JDK, the ME SDK, NetBeans 8 IDE, and then NetBeans plugin. The plugin gives you an emulator that then allows you to test what you're doing, even if you don't have a board, external board that you're going to be running your applications on. The emulator can test what you're writing in Java ME. But then if you have a board or some device, the emulator will then download the code into that board, and you can test directly on the board, and I'll show you that. So in the course, it also has some instructions in the form of a tutorial how to create a bootable image for your Raspberry Pi on the SD card that comes or that you can buy with it, and how to set up the Raspberry Pi as a headless, that is, without a user interface, embedded device, etc. So you can go through that. This is the simplest of all what we call midlets, the Java ME applications. And so we have lifecycle methods. One is start app and one is destroy app. So when the app starts, then the start app runs, and then you can put things that you want to, and then when it's time for the app to leave, then it calls destroy app, and then you can do some kinds of closure things. So the project in the MOOC is this case study in which we have this truck that takes vegetables and fruits from the farm and holds those and then transfers those to maybe a grocery store. So through that process where it's It's being loaded onto the truck and the doors are opening. And then as it's being transferred, we want to monitor the temperature and the humidity and the pressures. We also want to know where the truck's been, and even if it were a plane, for example, what the altitude has been. And we want to be able to store those things so that when we get to the supermarket, we could take a client display, perhaps in this case written in Java FX, and then establish a client-server session to the embedded device, our Raspberry Pi, and then display the data. So that's the case study that I'm going to take you through. And in doing that, if you see the things in blue, you'll see that we're going to talk about what GPIO is, which is general purpose I/O. We're going to talk about I2C, which is another communication protocol. We'll talk about GPS and UART. UART is another communication protocol. The way that we store things is in the record store, in the record management system, which is something that's unique to Java ME. And then we'll be talking a little bit about Java FX and tying that together. And so that's where we're going right now. So first of all, GPIO and I2C. So we'll talk about the first two boxes, GPIO and I2C, to catch the door open and closes and the pressure and temperature. So first thing in this lesson, we want to get started with the hardware, give you an overview on GPIO, and also give you an overview and tell you how to work with I2C. So for lesson 2, the ingredients that we have for putting things together are things like LEDs, light-emitting diodes. Everybody knows what those are. Maybe you don't know some of the details, like the long lead is called an anode, and the short lead is called a cathode, and the voltage runs from positive to negative, and that's some of the anatomy of an LED. And then we have resistors. Resistors regulate the flow of electrons. And so you want to use resistors to be able to control your amps, control the current. And then we have switches. Switches are things that open and close a circuit. And in our case, we're going to be using a momentary switch, which means when you're pressing it, it closes, and when you release it, it opens. We're also going to be using a barometric pressure and temperature sensor. And here are some of the specs. It can sense some pressure in that range. That's the resolution. The operational range for temperature is -40 to +85 C. It's accurate to ±2 C. Also, that hardware uses I2C to communicate, and then it uses 3.3 and 5 volts. So here are some of the hardware we're going to use. We've got a breadboard on your left. We've got some jumper cables that plug into the breadboard. And then we've got this breakout. Now there's 26 pins on that breakout. That plugs into the Raspberry Pi 26-pin header and then goes over to the breadboard. And you'll see that in a second. The ribbon cable is what connects the two. And there's a picture of a sample hardware on the right hooked up to the breadboard, and then the Raspberry Pi on the left. Now there are some things in this breadboard, there are a lot of holes in it, but underneath the holes, certain of the holes are connected to other ones to make it very convenient for you to put together circuits. So a little bit about GPIO. It's basically, it works with pins. So each pin can be either on or off, and then you could take a group of pins and add up the binary or multiply the binaries, and maybe with 4 pins you could have 16 states, for example. So the code you use here, if I use the device manager in the device I/O library of Java ME, and I can say open, and that's GPIO pin 1. Or I could open a whole port. And then I could set the value of that pin to true, or I could set the value of a port to some value. And so that's changing the value of that pin. So the GPIO pin interface gives you methods for controlling a particular pin. You can have input pins and output pins. So output pins are for writing. I might control an LED with an output pin, turn a light off or on. But also I can read an output pin, so I can see its current state. If I wrote a 1 to it to turn a light on, I could read it and find out that its state is 1. But input pins are only readable, and there are the constants on the third line, the constants for input and output. Now, to get the value of a pin, a GPIO pin, then I could either register a pin listener, or I could do some polling. So here are the GPIO pins on the Raspberry Pi. They're in green, so we have 8 of them, and they're numbered not contiguously. And they're also, note that they're different than the actual pins on the header pins. So that makes it a little bit confusing. But, and then we have other, if you notice over on the right, we have other kinds of I/O, like UART. If you look at pins 8 and 10, you have UART. And if you look at another thing we're going to talk about is, I'm looking for SDA, SDA, pin 3, SCL, pin 5. That'll be some I2C things that we'll be talking about. So to turn an LED light on and off, we need a switch and we need an LED. So if you look at the circuit, in the upper left is the number 1 pin. That's power, that's voltage. And so notice it's going through the switch and then through a resistor and back to ground. Pin 6 is the ground. And then also notice we have another circuit. Well, we have also a wire going to pin 11, which is GPIO 17. And then we have an LED with a resistor. So we have 2 major circuits there. And notice, the thing I want you to notice about this is that although we're wiring up the switch and the LED, you don't see wires that provide any logic for when this switch is closed, light the light, etc. That's all going to be done through your Java program, and that's kind of the point. That's how this works. So in order to configure a GPIO pin, you would use code like this. So we have the button pin, which was GPIO pin 17, and then we have the LED pin, which was GPIO 23 over here. Okay? And so the block of code that we say new GPIO pin config, that's where we're going to configure the characteristics of that GPIO port. That's the button one. So the characteristics that we're going to configure is which pin is it, which GPIO pin is it, that's 17, and then whether it's going to be input or output or both. In this case, it's just going to be input. And then the mode is going to be default. I won't go into what mode is. And then the next one is trigger both edges. That means trigger an input when I close the circuit and when I open the circuit. And then the default value, the default state of that pin is going to be false. So now we're set up for using our switch. And then for so then the next line is button. We're going to use the device manager open, the static open method, and pass in this config, and now the button is set up. So then with the LED, we're going to do the same thing, but we didn't have to use the config because the LED is very simple. We're just associating the LED with a particular pin, and if the pin is high, then the LED should be on. Pin is low, the LED should be off. And then we're setting an input listener. And then when the value changes, close or open, then the value changed method is going to be called, passing in the event. We can get the device from the event, which is a GPIO pin. then we can say, okay, if the pin was button 1, then we're going to toggle the value of the LED. So that's the wiring. That's the wiring in code, how we bridge the gap then between the switch being open and closed and the LED being lit. Okay? So this is a kind of a session here where Angela Saikedo, the person that created this part of the course, is going in and kind of showing you all the things that you need to do in development. So first of all, she's doing a PuTTY session, just a TTY session, and connecting to the port of the Pi, a console port of the Pi. And she's changing the directory over to the Java ME distribution. And then she's running a program called user test. And that starts a virtual machine and starts a process that then when the emulator connects to it, it can then receive a program downloaded into it. And then over in NetBeans, we open up an emulator. Now, in this case, the emulator is not there. It didn't appear. So we're going to connect to the IP address of the Raspberry Pi. And then it's the emulator, this embedded emulator, is going to appear over on the left. And then we can open it and see the emulator itself. And so after we've kind of taken a look at the program and noticed that in the program we've got things like the Start app down at the bottom. The content of this program isn't important right now, just the process here. So we've got different things in there that we're going to do to turn on a light when a switch is, or when the program starts up. But then we're going to go ahead and run the program, which is going to blink that light 8 times. So when we run the program, it's going to bring up the emulator. So we'll see the emulator come up. And at this point, then, because it's an emulator that's representing and connected to an embedded device, it's actually going to download the code into the Raspberry Pi and start running, and now we see that blink 8 times. Okay? So that's that. So then in the MOOC, you have different homework. So one of the things is creating a door sensor, and that is kind of that first block in our block diagram of our case study. So this is what's happening with this door open close sensor, and this is the homework assignment is to make that happen. So the idea then is to show the door status via LEDs. If the door's closed, then the green LED is going to be on. If the door's open, we want to turn the red LED on, or even blink it if you want to. And then this shows the different pins in the solution. You don't have to use those pins, but these are the ones that the class solution uses. And so this is the wiring, pretty much like the other one, except for we're adding another LED in the mix. And then this is the breadboard. And I'd like to take this opportunity with the breadboard to show you some of the features of the breadboard. First of all, if you look at the bottom row, you'll see that it says GND. That means ground. So that whole row is connected to itself. The whole row is, all the hoses are connected electronically. And so if I put that white wire in there, for example, then that's going to be automatically connected to that other white wire. Okay, so that's a ground. Then the one above that is 3 volts. We're using that for 3 volts in this case. And then at the top, we have the same scenario, ground and 3 volts. And then, I mean, you can do whatever you want to with those strips. That's the way we're using it in this case. And then in the middle section, you've got 5 rows horizontally. A, B, C, D, and E, and those are connected vertically, right? So each 5 are connected vertically, and then in that block, and then in the bottom block, F, G, H, I, J, those are connected vertically as well. And so in that manner, for example, that red wire on the left, that's actually connected to the bottom part of that switch. When you close that switch, then the upper right-hand corner of that switch, then the electricity is going to go through that resistor to ground. So that's kind of how our breadboard works. And it's really easy to use a breadboard. It's a lot easier than soldering wires. So you want to use a breadboard so that you can change things, or maybe even you want to, you made a mistake, and instead of having to unsolder a wire, you can just change things around on a breadboard. So now that we've discussed GPIO, I'd like to give you an overview of I²C, and that is what we're going to use to talk to the pressure and temperature sensor. So here's the pressure and temperature sensor. We already saw this. And I²C is for being able to move data between peripherals, or between a motherboard and peripherals. So you want to be able to talk between the two and send data, like 7, 8-bit data. So it's a serial kind of interface, but it's synchronous. What synchronous means is that there's usually a clock cycle that happens, and with each clock pulse, then some data is sent. And so both sides are using the same speed, and they're using the same clock pulse. So we've got a data SDA line, and we saw the SDA on the pins, and that data is sent along with the clock signal, which happens on the SCL line. And so the clock signal controls when the data is changed and should be read, and it's bidirectional. So I²C means inter-integrated circuit. It's also called two-wire interface because there are only 2 wires, and it was invented by Philips. And here's the design. So we've got a master, and you can have more than one master if you want, and then you've got slaves. The master is the one that turns on, that generates the clock signal, and then communicates with the slaves. Slave could be peripheral devices. And then the slave receives the clock signals and then responds, either with acknowledging that it's being talked to, or acknowledging that it received data correctly. And then you can switch between masters and slaves. So here are some diagrams of how the pulses go. But if you look over on the left, if the master wants to initiate some communication with a slave, then what it'll do is, while the clock signal is high, then it'll bring the data signal from high to low. And that means I want to talk, right? I want to talk. I'm reserving the bus. I want to talk. And then it starts sending information, and I'll go into what that information is. Then when it wants to stop, while the clock signal is high, it brings the data signal back high. So that's the overall. And then going down a step, then once it's started, then what happens is we've got clock pulses on the bottom from the master. And then if you look at the top, then we've got some data happening, the data coming out. And then at periodic intervals, after a byte has been sent, then the slave, the receiver, is going to either bring the data line low to say, I acknowledge that I received it, or it'll keep it high, and in that case, it's not acknowledging successful communication. And then here's actually how the communication happens. Again, we start, and then the first block there, address, read, write, ACK, that's the master saying, okay, I want to talk to some slave, and this is the address, and this is whether I want to read to it or read from it or write to it, and then that's where the slave would acknowledge. And so then we have the same thing for data, and then acknowledgement until we're done. So I2C is not enabled on the Raspberry Pi by default. So if you want to use I2C, then you have to go in and do some editing of some files. So in etc modules, you would add those two lines to enable I2C. Also, there's some helpful tools for being able to see what I2C devices are connected. And so to install the tools, you just use that line, install I2C tools, and then the I2C is blacklisted by default, so you need to comment out the lines in that file, those two lines in that file, and then you'll be good to go for I2C communication. Then there's a tool called I2C detect that you can use then to find out for all of the addresses what I2C devices are there. So see, we have one at hex 40 and hex 70. So then using I2C on the Raspberry Pi, the Raspberry Pi uses I2C bus 1, there's two buses, and we're using, for our temperature sensor, we're using hex 77 address. Now the I2C uses 7 bits for device addressing, and it uses a clock, the BMP 180, our temperature sensor, uses a clock speed of 3.4 megahertz. And the control register, I'm going to tell you what that is in a second, but the control register for the BMP 180 is hex F4. And the temperature value, if I want to know what the temperature is that it's reading, that's at register F6. So these I2C devices, this particular one, has registers that I can read and write into. So I'm writing into one to say, give me the temperature, and I'm reading one to read the temperature. So this is the wiring for that particular, for the temperature sensor that we're wiring up here. And this is the code for how I would read and write to this particular device. So the bus number is 1. I'm just repeating what I did, the bullet points here. The bus number is 1. 77 is the device address. 7 bits in an address, the clock frequency. I'm going to go ahead and open that then, the device manager open. And then here I'm writing to the control register F4, 1 byte, and I'm writing the get temperature command. 2E means give me the temperature. And then I'm going to read from the temperature register, where the temperature is stored, 1 byte, and I'm going to put then this series of bytes that represents the temperature that then I can manipulate to find out what the actual temperature is in Celsius. So that was I2C. So now we're going to move on to GPS, global positioning satellites, and then UART. We're going to use the UART communication protocol to talk to our GPS receiver that's in our that is going to be connected to our Raspberry Pi. So we'll talk about UART, we'll talk about GPS, how to connect it, how to read, and that kind of thing. So UART is a serial protocol. Does anybody remember using like Hayes modems or anything like that? Okay, so keep your hands up. If you've used 9600, if that rings a bell, okay, 4800, 2400, 1200. Oh boy, just the old people. Where did I leave off? 1200? Okay, 300, 110. Any 110s? 110. Okay, so yeah, so you're really old, or have played with some old hardware. So 110. I remember dealing with 110 in the circumstance, I guess, of having a phone, like a handset, like a wired phone handset, putting it in an acoustic coupler, right? So that the bits were actually going audio over the phone line, And that was the first one I've used, and my colleague over here has used, was actually 110 baud. So anyway, so that's UART. That's kind of the, so if you've dealt with UART or Hayes modem protocols or anything like that, you know that you have some bits, maybe 7 bits, 8 bits, a parity bit, a start bit, a stop bit, maybe 2 stop bits. That's the idea. So you're putting bits over the wire, and you're either doing that through sound or electricity. The UART itself doesn't usually transmit the data, but you use some other protocol like above it, like RS-232, for example, with the modems, that actually transmits the data. But you could also transmit it with Bluetooth or infrared, or as I just mentioned, acoustic modems. Now, GPS, we're going to talk to the GPS receiver, but GPS, and you all know this, I'll just breeze through this, but you have satellites in the sky, and then your position is calculated by the satellites broadcasting their location and the time. And then if you get 3 satellites, you can get a position fix. If you get 4 satellites, you can get your position, lat lon, and your altitude. So then there are standards for the data formats for GPS receivers, and we're just basically talking now about how do I, from my program, how do I then get the GPS information from this just GPS receiver. So all the messages start with a $, they start with GP, that's the talker code, and then there's 3 more digits that mean this is either position or velocity. And so we have these different data packets that are in the course. And then you need to parse that. So you could use string tokenizer, you could roll your own CSV extractor where you're pulling out tokens between commas, and then we need to remember about data encapsulation, where now we're going to do something with that data, so we're going to put it in maybe a position object or a velocity object. And so those kinds of things are considerations for when we write programs that are going to be reading these GPS devices and then writing them perhaps to some storage. So then we output the data. In this case, we're going to output the data to a CSV format, because in a next step, we're going to write that CSV data to our data store that's on the SD card on the Pi, so that later we can access it via client server from our Java FX program. So connecting the GPS sensor to the Raspberry Pi. We're going to talk to it through UART. Now we have 2 choices. We can either do UART through a USB adapter. It's a USB to TTL, a transistor to transistor logic adapter. Or we could have a direct connection to the Raspberry Pi header pins, the UART pins of the Raspberry Pi. So the Raspberry Pi has 3 USB connectors, a micro USB connector over there, and then 2 USB connectors there. So we could use one of those, we could wire up a USB adapter, and then we could use those pins, use those wires, hook one to ground of the Raspberry Pi, one to ground of the GPS receiver, one to voltage, and then TX and RX, that's transmit and receive. But we switch those, right? Because transmit you want to be hooked up to the receive. So transmit on the Pi to receive on the GPS and vice versa. So that's what we're doing here. And then an alternative is we could use the UART pins. So there's the Raspberry Pi headers. We've got some connections. And here are the UART pins. Those are the ones in orange. And those are transmit and receive. So we could hook it up that way too. So we have 2 options when we're using UART. One is the USB through a USB port using an adapter. The other is straight to the UART pins on the header. And then this just talks about some UART configuration that you could look at when you look at the course. So now if we are going to read the data, we simply use the device manager that we've seen before. It's in the device I/O library. We're going to open 40, open port 40. 40 is the UART ID number. We're going to set the baud rate, and then we will create a new input stream with the UART, calling this new input stream a static method of channels. That gives us an input stream, a very familiar Java input stream. Then we can wrap that with an input stream reader, and then wrap that with a buffered reader to take it from 8 bits to 16 bits, for 8 bits to Unicode. So then we have some security considerations where we need to give it device management permission, and we do that in the emulator. And then this is some considerations in reading GPS data, where data lines start with a $, and the different things that I talked about before, GP, GA if it's position, VTG if it is velocity. And just a note that the data from that device gets easily corrupted. So you need to have some error handling, because if you got a corrupted piece of data, then just read the next line. So then we're going to, once we have the data, we're going to save it into the storage. So there's a couple ways to do that, and I'm going to show you that. But first I'm going to kind of talk about this concept of suites. We have these midlet suites. Midlets, remember, is a Java ME application, but you can have them in suites, to where, in this case, for example, we have this recorder midlet that is recording and reading these sensors and recording that information and then putting it into this RMS data store, and I'll talk about that in a second. But we have another one where we can read it to verify that we got it. And as you'll see in a few minutes, we've got another one called a server midlet, so when we connect to it from the client, from this JavaFX client, it's going to send us all that information. So those things are all in one suite, and they can share a data store. So record management system overview, because of this size, Java ME does not rely on the idea that the small device even has a file system, but it does provide for an RMS, a record management store, so it abstracts that idea, and it's a very simple record management store. It's got 2 columns, a record ID and then an array of bytes. You can have that array of bytes can represent anything you want. You can structure that however you want to. So to open a record store, you pass in the name of a record store, GPS data in this case, and then true means if it doesn't exist, go ahead and create it. And then here we're going to read some data bytes out of it. And then we're going to add records into it. Once we've read them, then we're going to add records into them. So it's very straightforward. And so we can create a new midlet in the same midlet suite as the data recorder, and that other midlet we could read from that same record management system. So there's the code for doing that. And then as soon as you shut down the suite, then the data store goes away. Also, you could store data if the embedded device has a file system. You could store the GPS data in a file, and you just need to be careful with the file URI, in that you need to say file : and then give it at the root of the file system. And that's part of the generic connection framework that's also part of Micro Edition. The generic connection framework allows you to connect to files, to HTTP, to raw sockets, to to streams, any kind of stream. And so that's the file connection. Then you need to also give it permissions to be able to read and write to files. So then communicating data to the outside world, we're now all the way over to the right, where we've got this client display with this application that we've written in JavaFX, and we've used Scene Builder to do that. And these college students will be showing you an application that they wrote as well, using Java, using the JavaFX API and Scene Builder. And as they come up here, I'll go ahead and show you this last couple bits here. So we've got these two pieces of this prototype puzzle that we're dealing with. Over on the left, we've got the data recorder suite, this midlet suite. We've got the recorder that's getting all the data. We've got the reader, if we wanted to see what data we've received. And then we've got the server, where this JavaFX client can connect to it over a socket and then send it messages and then receive that data stream and then graph it. And so that's what you'll see here. So here we've got a NetBeans application. It's a midlet. We're starting up the data recorder, the recorder midlet. And then we'll see the emulator come up. Now notice this is the console of the Raspberry Pi. And so now we'll go ahead and start the visual client. That's the Java application using the JavaFX API. Now we're going to start the server midlet, and that's going to listen for a connection, a socket connection. And then we've connected. Notice it said connection received. Now we're going to read data. Now it's going to spit out data from the RMS data store and graph it. Graphing it, it turns out, is very easy with the JavaFX API. And then we'll go ahead and disconnect, and that'll send a disconnect message to the Pi, to that process, after we look at this table of positions. This is the information that was read while the devices were hooked up. And then we disconnect, and then we could connect again if we wanted to and read some more data. So now I'd like to turn it over to my colleague, first of all, Stephen Van Impe, who is their professor, and then the four students that have created this application in JavaFX where they won a programming contest. And my colleague Yella Ilat will be telling you all about this. So please give them a warm welcome.
So, good afternoon, everyone. First of all, I'd love to thank you for giving us the opportunity to present our project for you guys. My name is Jelle. This is Dan, Lucas, and Wout. And we are students of Applied Computer Science in Ghent. This is our teacher, Steven Van Impe. Every year in our school, we have to make a school project, because after all, that's how you learn how to program things. Last year, we were given the opportunity to choose between Java Swing and JavaFX. In our first school year, we had some experience with Java Swing, and we had absolutely no knowledge about JavaFX, but we still chose JavaFX to use in our program. JavaFX looks like a really promising platform for us, and after all, we're still students, so we had really nothing to lose, just learning new things. I'm now giving the word to Lucas and Wout for presenting the application.
All right, thanks, Jelle. When we started out with the project, we started in Scene Builder, which is a program that quickly lets you compose a user interface with a drag and drop utility. Our application was actually built to manage theses of students and to, you could link promoters with certain students. And so we built the main structure with Scene Builder, which is the components that Wout is showing us right now. For example, a simple table view. When we started digging into the code some more, we found that implementing a filter and the sort feature was very easy. We also did so, at our school, you've got two completely separate campuses, Aalst and Ghent. Those are other lists of students, so we made it easy to switch between campuses. It's a global switch that lets you choose between two lists. Another feature we implemented. Then that was an example of a table view right here, but we've also got an example of a tree view. You've got for the theses, you've got different research fields, so the administrator could add, with very basic functionality, he could add some research fields. And as we acquired some more JavaFX skills, we actually stumbled upon JFXtras, which is founded by James Weaver and Stephen Chin, your speakers for today, which is a big coincidence actually. And then we experimented with one component specifically, which is a calendar view and is developed by Tom Eugelink. I say experimenting because we didn't have the time to fully implement it, but the idea was to have a combination of a table view and a calendar view, where you could drag and drop a student and his presentation onto a calendar, where you had the time slots of promoters visually laid out and stuff like that. So to conclude, we can say that JavaFX is a very flexible platform with a low learning curve, and that we would choose JavaFX over the old-fashioned Swing anytime. If you guys have some questions for us or you want to get in touch with us, just give us a shout, and thanks.
Thank you very much. Yeah. Okay, I'd like to now bring to the stage a colleague, Robert Savage, who is actually the founder of a library called Py4J. So,
thank you. Give me 1 second while we get set up here. We're going to make sure everything is turned on and switch to our input. And one quick check. All good. Okay. So first of all, I'm thrilled to be here because I get to share with you a hobby project that I started 2 years ago that I never could have imagined would have gained acceptance, popularity, and usefulness. It's amazing for me to see. I went to Java 1 in San Francisco this year, and I was just shocked at how many IoT presentations were given around the Raspberry Pi, and they were using Py4J. So it was kind of cool to see your baby grow up and be used in the community. So the Py4J project, whoops. The Py4J project, let's get a quick show of hands. Is anyone in the audience familiar with Py4J? Okay, a few. Well, then I've got my job cut out for me to share with you what it is, so you walk away, everybody, understanding what Py4J is. So when the Raspberry Pi platform was first announced, I was one of the kind of early adopters to get on the wait list, and I was really excited about this platform. I've worked in the home automation and business building automation community for about 15 years now. But when this device hit the market, I was just amazed because this is a very empowering device. This is a platform, a very democratizing platform that's accessible to all of us. Prior to the Raspberry Pi, if you wanted to buy a development board and do custom development on it, you're talking several hundreds, if not thousands of dollars. Now that we've got a device in our hands that's $35 US, that's an incredibly powerful platform. And the fact that it exposes GPIO, I2C, SPI, and serial communications allows us to use this device to interact with our environment. So what Py4J is, it's a fully open source library. You can use it on Java SE, which comes on Raspberry Pis now out of the box, thanks to Oracle and the Raspberry Pi Foundation for getting that in there. It's an open source project that provides a low-level I/O access library to the hardware. So the header pins that Jim was showing us that have the different GPIO access and I2C and SPI, those originally weren't accessible to us as Java programmers. We would have to go through native code to access those things. So what I wanted to do as a means for me to give back to the community, I've certainly enjoyed the benefits of all of the community efforts and the open source projects. So my little niche of the world that I tried to carve out was providing something back to the community by creating this library that we as Java programmers could promote the use of Java on the Raspberry Pi platform to build things that we can interact with the real world. So again, Pi4J, open source, low-level I/O access library. And then as I was designing it, I thought, well, as Java programmers, we're very object-oriented. We want to model things after the real world. So the style of APIs are very object-oriented, where you construct objects and interact with those classes. And then the other interesting thing that Pi4J added was event-based interfaces, so that if something occurs on your GPIO pin, we event that to you in your Java program. More traditional I/O access libraries, you'd have to poll for that or do something like that. So we wanted to eliminate those kind of barriers and make it very simple for Java programmers to consume the I/O capabilities of the Raspberry Pi platform. The Pi4J project is written completely in Java with a side helping of some C native code so that we can access some of the lower level functionality and optimize for the Raspberry Pi platform. But fortunately for you, you don't have to access any of the C code or worry about the J and I. That's all buried underneath the covers for you. So you get a nice Java library with Java objects that you can interact with. And what we're going to look at today are some of the capabilities of this platform and how we would instrument Pi4J on the platform and build some real-world projects. So I mentioned earlier that the Pi4J project supports GPIO, Serial, which is the UART communication, SPI I2C, and there are some analog concepts in Pi4J. Although the Raspberry Pi hardware doesn't have any analog inputs or outputs, you can augment the circuitry by adding some additional add-on boards that you can access analog. So there is some basic analog functionality in Pi4J. But today, for our demonstration here, we're going to focus on GPIO and then serial communication. Okay, so some of this will be a little bit of a recap from what Jim told us, but we're going to focus on it from a Pi4J perspective. So GPIO, in general, these are just the I/O access pins that are provided to us on the header so that you can use that pin for either an input or an output. A GPIO pin is a binary pin, so it's represented in two states. It's either high or it's low. Fundamentally, that's what it is. There are some more complex pulse width modulation things you can do, but for the sake of our conversation, let's just keep it simple, and we have simple inputs and outputs that are either high or low. Now, based on the different models that Raspberry Pi provides, there's several models that they have released. There's different numbers of GPIO pins that are accessible to us. So the first models, the Model B and the Model A that were published, have a 26-pin header. But the newer models, the B plus and now the A plus as of Monday, have a 40-pin header. So that offers more GPIO capability to us. The Pi4J project supports all of these models. I do need to get an A plus model in for testing, but it should work. And then the compute module, which I thought was a very interesting introduction by the Raspberry Pi Foundation, because the compute module is a piece of hardware that's designed that you can build your own circuitry, your own carrier board for, and you pop a Raspberry Pi in it, and now you can have your own powered hardware with your own custom circuitry powered by a very powerful little chip. So to access the GPIO pins from Pi4J, you have to understand the addressing scheme. Now, there are several different addressing schemes that different libraries use, and Pi4J is based on a C project called Wiring Pi. So we've adopted the Wiring Pi numbering scheme for use in Pi4J. The numbering scheme that Wiring Pi uses is an attempt to abstract the pin addressing from the actual hardware. And in early models, the actual GPIO pins moved around in some of the early B models. So Wiring Pi, and thus Pi4J, was able to keep that change from you as programmers. You get to use the same address number. You don't care that it moved around on the board. So that's one benefit to its numbering scheme. Again, there are a variety of different Raspberry Pi models. You can visit pi4j.com, select the model of Raspberry Pi that you have, and then you can view a pinout mapping of all the different pin numberings to understand what pin address you will need to use. So first we're going to talk about GPIO outputs. GPIO outputs are the simplest of the two, and effectively you have this output pin, and you can control or signal it either into a high state or a low state. And we can use that GPIO pin to control things in our world. Control lights, buzzers, motors, things that we want to turn on and off. So GPIO outputs are perfect for that. The simplest circuit, and we looked at an example of driving an LED in Jim's presentation, so this is not any different, just a different form factor. But I guess it's important to note that the GPIO pins are very low level voltage. They produce 3.3 volts when you signal a GPIO pin high. So you can drive very simple circuits like an LED that only requires 1.5 to 2 volts, but you can't power something that either requires higher voltage or ample amount of current to drive something like a motor. So what we have here in our demo board, which we'll come to in a minute, is we're going to control some things like a strobe light and buzzers and an illuminated button ring. We're going to control those, and those are higher voltage devices. Those are 12 volts devices. So we're going to control that through some additional circuitry, and we'll come back to that. But first, let's take a look at what the Pi4J code looks like. So what we're looking at are Pi4J interfaces and Pi4J classes. And this is how you, as programmers, would use the Pi4J library to control something, to make a GPIO output pin, and then to control it. So first, we need a GPIO controller. And we have a factory pattern where you can use a GPIO factory class to get an instance of that GPIO controller. We use a factory pattern because you only need one GPIO instance anywhere on the platform. We don't want to provision pins for multiple purposes and steal their capabilities elsewhere in the project. So once you've provisioned a pin, it's kind of reserved for your usage. Once we have got our controller, we can then instantiate a GPIO pin digital output. So we've got a simple variable named output that's going to adopt that interface. And we use our GPIO controller to provision that output pin. And as arguments, we simply pass in the address that we want to use. So in this case, GPIO 12. And then what default state you'd like it to come up in this case, low. So we're going to use GPIO pin 12, and when the system boots up and this object gets instantiated, we're going to drive that circuit low. Now, once you've got your output object created, now you get to have functional commands that you can, or functions that you can execute against it to make it do things. And commonly for GPIO outputs, that's going to be either .high or .low. You're going to signal the GPIO pin to go high, 3.3 volts, or low, 0 volts. There's also some utility functionality that we have in the classes that provide things like toggle, which would invert the current state. We've got pulse, which you can pulse to a specified state for a duration of time. That pulse can be blocking or non-blocking, it's your option. And then there's some additional functions that we have, like blink, if you want to set up a repeated kind of blinking concept, and we'll look at that in our demo. So back to the point about driving higher voltage or higher current circuits. So on our demo board here, we use a relay, an additional relay board augmented with our Raspberry Pi to control these higher voltage circuits. We control a 12-volt strobe light, and we're going to control a 12-volt illuminated button ring. So simply, when we want to wire that up, we provide power and ground to the relay board, and then we have our two GPIO output pins wired to the inputs of that relay board. So when we drive a GPIO output pin high, that can actuate the relay. Now, on the other side of the relay, that's where you hook up your high voltage circuits or high current circuits that you want to actually control your equipment with. So with a very simple circuit board like this, a very simple relay board, you can control a wide variety of things. Other than a relay board, you could use more sophisticated circuits that are transistors or solid state relays. There's other options, but this is a very simple example. So why don't we take a look at what that looks like in code. So we're going to run a very simple demo. We are going to, first of all, I'm using NetBeans. The latest version of NetBeans has excellent support for the Raspberry Pi. You can configure the Pi over the network as a remote platform. So when you create your project, we import our Pi4J libraries, we write our code, we can run and debug directly from NetBeans, which is awesome, because prior to this, we would have to compile the code or send the code over to the Pi via SSH or we have to get it over there somehow, and then we have to compile the code and run the code. And in prior demos, prior to having this capability, I would usually have a shell session up to do everything manually, but it's awesome that we can run everything directly from NetBeans. The only caveat is it takes a little bit of time to load. So I'm going to go ahead and fire up the program, and it's going to load in the background, and while that's going, we're going to kind of talk about the code. So here you can see we have our GPIO controller that we got from our factory, and in this case, we're going to actually instantiate two output pins, an LED pin and our strobe light pin. We can set some optional shutdown options so that if the program were to abnormally terminate or just gracefully terminate, what state do you want the GPIO pins to go back into? So it kind of gives you a safe state to revert the pins to. And once the program's running, what we'll see here is that the strobe light is going to set that pin high, which is a constant on. And then on our LED button ring down here, we're blinking that every 250 milliseconds. So you can see, and then our program's going to run for 15 seconds and then terminate. So you can see there's very simple objects that we accessed, and we control this relay board, and then it controls the devices that are our ultimate targets. So that's pretty much it in terms of coding a very simple GPIO output. You can see how easy this is. So we are going to switch back and now talk about inputs. So the opposite of GPIO outputs are, of course, inputs. Inputs allow us to monitor things in our real world or sense things in our environment through physical hardware devices. There are things like flood detectors if we want to detect moisture, maybe in our basement or in the HVAC system. There are water level sensors, and this is an example of a water level sensor. As the water rises, a float raises and trips that circuit. There are examples like door sensors, magnetic door sensors, so you can understand whether it's open or closed. Proximity sensors, and then we also have a IR beam break sensor. So this produces an IR beam that's reflected back, and as long as the IR beam is not interrupted, then when the IR beam gets interrupted, we can trip a state and understand if there was a change. So these are the kind of simple binary on-off conventions that we can use GPIO inputs to monitor. So first we'll look at just a very basic circuit so we can kind of explain how it works. So functionally speaking, a momentary switch is just a very simple input device. When you depress the button, we close the circuit. When you release the button, the circuit opens up. So in this example, we're sending our 3.3 volts from the Raspberry Pi header pin as our source signal. We're sending that through the momentary switch and then back into a GPIO pin. So what happens is when you depress the button, the circuit closes, and the 3.3 volts actuate the GPIO input pin and signal it high. And then when you release the button, it signals back to low. Now, there's one caveat to input pins, and when we're speaking about a GPIO pin, we configure it as an input or output pin, but it doesn't know if it's supposed to be high or low. It needs some kind of reference. So in the absence of your circuit providing it either a high or low signal, we need some kind of weak reference so that it knows what to gravitate towards. Without a reference voltage, the GPIO pin can float, which would cause some very erratic behavior in your program. So this reference is notionally known as either pull-up resistance or pull-down resistance. So depending on the design of your circuit, you're going to need either pull-up or pull-down. Now, fortunately, on the Raspberry Pi platform, they provide us internal pull-up and pull-down resistors. So we don't have to necessarily design that into our circuit. We can just use Pi4J, and when we're provisioning our input pin, we can tell it, do I want this to have a pull-up resistance or pull-down resistance? So when would you use each? If you're designing a circuit that's going to drive the voltage into an input pin, and you're going to signal that input pin into a high state, then you need a pull-down resistance. What that will do is give it a weak reference to 0 volts. So the pin will default to this 0 volt ground state, and then when your circuit completes, we're going to signal it high with the 3.3 volts. And the converse of that would be pull-up resistance. If you're going to provide a ground circuit to signal the GPIO pin low, then you would use pull-up resistance. Optionally, you can also totally build this into your circuit. You don't have to use the ones built into the Raspberry Pi, but that's an option to you. This is an illustration of how you could design that into your circuit without having to worry about it on the software configuration. But for our example, we are going to use the internal ones. They're simpler, and for demo purposes and for prototyping and hobbyist usage, they're great. So here is what the Py4J code would look like for an input, GPIO input. Again, we have our controller that we created from our factory. We instantiate a GPIO digital input pin, and then we use our controller to provision that pin, giving it the address of the pin that we're targeting. And then here's where that pull up resistance or pull down resistance configuration resides on the third parameter. So input pins, we also want to understand when those states change. So I mentioned earlier that Py4J provides it's an event-based API, so we provide listener interfaces that you can implement to understand and react to those state changes rather than having to constantly poll it. So since we're in a Java 8 conversation, we can certainly use a Java 8 Lambda expression on this input listener, or if you're using an older version, you can certainly use an anonymous function here. And in this example, we're going to take our input and we're going to say when this input state changes, we want to now take that change and set our output device to the same state. So if the input signal goes high, from software, we want to tell the output state to go high. If it goes low, we're going to set it low. So what that's going to look like is, let's go ahead and fire up demo 2. And we'll take a look at the code real quick. And we're going to build on the existing examples we've already started from. So what you see here is we already have our controller and we have our, can you guys see the code okay? Everybody okay? Okay, so we're going to add ourselves a GPIO input pin, and we provision that pin, give it an address. You notice I didn't here give it the reference. There is a default that it reverts to, so I'm just using the default configuration. And we have our shutdown options, and then here's our new listener. And what we're saying here is this is that change listener so that when the input pin goes high, we're going to drive the outputs high, and the converse of that. So if we look at it, our program is started. So what should happen is I have a momentary switch down here at the bottom of this board, and that's what I configured as our input pin. When I depress this, the signal is going to signal the input pin high, and then our software should tell our two output pins, our strobe light, and the LED ring around the button to light up. So let's see if that works. Oh, excellent. So our strobe light's on, and our little ring is illuminated. And when we release it, of course, goes back to the low state. So very simple, but we're just kind of going through the basics to see how you can get started using this stuff. So we'll go ahead and kill that. Okay. We've talked about GPIO inputs and outputs, and they're great and simple and easy to use and provide all kinds of functionality to us. But I think another benefit that the Py4J library provides is a component layer API. And what this component layer API is it provides us object-oriented classes and interfaces that represent more real-world devices that we're controlling. So in my program, I really don't want to understand high versus low or deal with GPIO because electrically that circuit could change, and now I'd have to go throughout all my code base and change that logic if the circuit were to change. If I use a component interface, I can isolate those changes to just where I'm instantiating it. And functionally, I can operate on the component interfaces in a more conventional way with the objects I want to interact with. For example, I can have a light interface, or an LED interface, or a sensor interface. And what you'll see is that here are all the interfaces that we have today. This is a growing list, and by all means, if you have your own components that you need, we're happy to help out, or if you're able to contribute to the project, that's even better. And then here's what that might look like in code. So we already have our output pin that we created earlier. We're going to instantiate a light object, and we're going to use the GPIO light component class as our concrete class, and we're going to provide the output object into that constructor. So now that I've got a light object, I can operate on it very, very simply with a dot on or dot off. I don't have to worry about what high means or what low means or input reference or anything like that. That's all abstracted away where you provision your pins, but not now throughout my program, I can use this object more like a real world modeled object. And then our second example here, we have our input, which is a momentary switch. We provide our input pin, and here you can see where we can assign it the low state means off and the high state means on. Or we could easily, reverse that direction if that's what our circuit required. So if that were to change in the future, you could come back to where you're creating these objects and just change it there, but not throughout the rest of your program. So this is it really abstracts the implementation of the hardware that you're working with, so you don't have to proliferate your code with GPIO specifics. So we're going to take a look at that demo now. We're going to run this, and functionally, this demo is not any different than the one we just ran, but in code, what you can see is that here's all of our input and output pins, and now we're going to create our components. So we have our momentary switch component, which we've named button, and then we've got our light component and our LED component. So our light component's the strobe light, and the LED component's the little LED ring. Now when we look, we can add listeners against our component interfaces, just like we could on GPIO pins. So when our listener is activated, when this event comes through, then we can implement our business logic. So in this case, we're saying, if the switch got turned on, turn the light on, turn the LED on. Now let's turn them off. So that you can see this reads, it's easier to read, easier to understand, and it reads more like the problem statement or the real world condition that you're trying to work through or trying to implement. You can also add listeners to the other components to, if you needed to respond to, let's say, when the light changes, you also want to do something else, but maybe you have multiple points that multiple pieces in your code that activate that light. Well, if you just wanted to create some chain reaction kind of thing, you could just add a listener on that interface and implement your additional business logic. Here, we're just going to print out that stuff to the console. So if we are running, again, this demo is going to look exactly like the previous. When we activate the button, we're going to get the same strobe light and the same LED ring turned on, but we're using a component level interface rather than the raw GPIO interfaces. So we have that working, and you can see on screen that when we're printing out to the console, the states that are changing. So you can kind of understand that this encapsulation, this abstraction provides us a nice, convenient, readable way to use Pie4J and interact with the hardware. Next, we're going to talk about serial. We talked about this earlier in Jim's presentation. We're going to use serial from the Pie4J, from the Raspberry Pi in the Pie4J interfaces to control. We've got a little message reader here in the front that we're going to drive some messages to. So the Raspberry Pi does support the onboard UART that we looked at earlier. And then Pie4J supports the basic serial communication to communicate with that UART. Now, it's important to note if you're going to use an external device that probably communicates with higher voltage levels like RS-232, that it's going to require a level shifter. If you're interested in this and want to understand more about that, I have a blog article on my website, savagehomeautomation.com, that goes into more detail about implementing level shifters and RS-232 communication through a level shifter. But today, we're just going to use our simple USB to RS-232 adapter. Our Raspberry Pi has USB support. We can simply use this adapter to communicate with our serial device. So the Pie4J code, we instantiate a serial object. We use our serial factory to create an instance of that object. And now once we have our serial object, we open a port with our serial object, and we provide the port that we want to open. If we were using the onboard UART, we would use the default COM port, and then we can pass in our communication parameters like our baud rate. After we've opened the port, now we can actually write data to the serial port. And we can also add a listener so that if the device is responding to some interrogation command, or perhaps it's asynchronously sending you data that you need to monitor, you can implement this listener to then implement your own business logic to take action on the data that you've received. In our example, we're just going to print out to the console because we don't care about what's coming back to us. So, take a look at that demo real quick. I'm going to fire up this one. Okay, well that's loading. We'll take a look at the code. Again, we have our serial factory creating our serial object. We're going to open the port. In our case, we're not using the default COM port. We're using the USB port. Our baud rate on this thing is 2400. It's a fairly old device. Our serial listener is just going to echo data to our console. And then here's where we're going to write our hello world message on the output. I don't know if it's started yet. Nope, not quite yet. So it's going to print a hello world message, and then after about 5 seconds, it's going to switch to like a stock ticker. So this is just to provide an example of what that how you can send data to a device. Okay, so we've got our hello world message. That's our, what every programmer goes through first, and then we switch to our stock ticker. So here I'm just printing out stock data for different stocks. So you can kind of see this is just a basic example of how I can use serial communication to communicate with the device. The data that you see where we're actually writing to the device is a unique protocol specific to that device. So whatever device you're interacting with, it's going to have its own custom commands and own custom protocol. So you'll have to look at the documentation and the specifications for that device to understand how to talk to it. But that's kind of what we got here. So our output, our console output, you can also see that we've gotten some data back. So every time we sent a command, he echoed an acknowledgement back to us. So we've got data events that came in. Alrighty. So we are going to take everything we've learned today, our GPIO inputs, GPIO outputs, component level interfaces, and RS-232 communication, and let's build something real with it. Let's build something fun and engaging. So we're going to define a project goal to create a very sophisticated model rocket launching platform. So I think we're going to take a quick break, and then when we come back, we're going to go into the details of how we would create this model rocket launching program. It's about 2:50. Why don't we get back around 3-ish? We'll start probably 3:05, and then we'll go through the exercise to create our demo project. Thank you. Testing. All right, welcome back. So when we left, we just said that we're going to create a project from everything that we've learned. So we're going to do a little bit of recap, but we're in the context of building ourselves a project. So with any project, we have to start with requirements. So for a model rocket launching platform, I think the first and foremost requirement is that we need a launch button. So we have our launch button here. We've got our little remote detonator, remote launch platform. And I guess we should be somewhat security conscious. So we've got ourselves a security key that will arm the rocket to make it ready for launch. And in the absence of it being turned on, you won't be able to you won't be able to accidentally launch the rocket with the launch button. So launch button and safety key. Next, we may have spectators that are watching our rocket launch platform. So we want to, when we arm the rocket and we want to make it ready for launch, we want to notify both audibly and visibly, we want to notify the audience that there's a launch that's getting ready to take place. So in our demo board here, we've got a signal bell and of course our strobe light that we've been using. We're going to activate each of those when we arm our rocket. And then there are several abort cases that we have to deal with. First and foremost, we need a manual abort button. So if something were to go wrong after our rocket is armed, we need to abort to exit that state. We're also going to use our key switch, and we turn the safety off. That would also abort the rocket launch. And then finally, if we have someone approach the launch platform, maybe we want to automatically abort the system because it becomes an unsafe environment if someone approaches the launch vehicle. So we're going to use our IR beam sensor here on the top of the demo board, and if someone were to cross that path, it's going to automatically abort our launch. Since we have it, we're also going to display to the audience using our message board down below to show them what state we're in, if we're armed or if we've aborted, or show them the countdown of our launch. And we'll implement a countdown timer so that once we press the launch button, that will activate our launch sequence and start our countdown timer. And finally, we're in a Java conference. We've got Raspberry Pi, we've got Java, and we've got Java FX. So we're going to build a on-screen console dashboard using Java FX running directly on the Raspberry Pi. So we have that. And we're going to show our countdown timer and kind of a pictorial diagram of our rocket and what state we're in. So this diagram illustrates, oh, I'm sorry, I haven't showed you my slides. The wrong screen. My bad. So we'll back up just for a second. So we've got our launch button and key switch, our audible and visual cues, our abort button and the IR beam brake sensor for aborts, our message reader, as well as a countdown timer, and finally, our Java FX dashboard, which you saw through the talk I was just giving. And then finally, here's our wiring diagram, and you don't have to study this in depth, but just to understand kind of a pictorial diagram of the different aspects that we're including in this project and kind of how they get wired up and notionally how they're connected back to the Raspberry Pi. So let's just jump to demo code and take a look at it. So this is just a typical Java FX project. We created it in NetBeans. It creates a main class for us, which when the main function gets invoked, the static main gets invoked, we start our Java FX program. And in this case, we are using FXML, so we're going to use an FXML loader to load our layout. When our layout gets loaded, we have a configuration in the layout to also load a controller. And our controller implements the initializable interface. So when the FXML layout gets loaded, it's instructed to also load this, to initialize this controller class. And in the controller class is where we're going to include all of our business logic for implementing our rocket launch platform. So here's where we're going to kind of recap the lessons that we've learned and show how we put all this together to make a real-world project. So first we have our GPIO controller. We create our strobe light pin using a digital output pin, Then we use our light component to turn that into a component because we prefer to work with component interfaces versus GPIO. And additionally, for outputs, we've got our signal bell, which is using a relay component. We've got our abort button, the LED ring around the abort button, that is also an output, and we're using an LED component for that. And now for inputs, we've got our security switch that's on the launch remote, and it's using a toggle switch interface, which is also from our component library, and our launch button, which is using a momentary switch, our abort button, which is also using a momentary switch, which is the abort button here on the display. And then finally, our safety sensor, which uses a sensor interface from the component library. So you can see that we've provisioned all these digital input pins and output pins, assigned the appropriate addresses and default states and the shutdown behavior. And then we've instantiated components for each of those GPIOs to now interact in our program with the component interfaces. Now, behind the scenes, if you were to actually dig into the code, we're also doing some serial communication. I kind of abstracted that away so it'd make the demo read easier. But if you dig down into some of the classes and the business execution, you'll see where the serial communication is happening. So now that we've got our components, I've implemented all of the business logic in this program in our component listener interfaces. So when we execute the security switch, we turn it on or off, we're either going to make the launch ready or we're going to abort the launch. In the launch activation, where we're going to start the launch activation sequence, we're either going to, if our launch is ready, we're going to activate the launch, otherwise we're going to print out an error message. And then we've got our abort cases where if the abort button is manually pressed, we're going to abort the launch. If the safety sensor receives a high state, we're also going to abort the launch. And then these are just the functions that implement the kind of logic that we're driving here. So, without further ado, I think we should move on to launching our vehicle. So here's our console output, and now I'll switch over to the Java FX. And like any good Java programmer, testing is imperative. I wish I could say that in my real work life, but we'll say that here for the sake of our conversation, because we're going to test each of the cases that we just created. So, first of all, our first test case would be, we don't want accidental launches. So if I depress the launch button, hopefully, we won't be launching our rocket. Excellent. So use case 1 complete. Number 2, we want to test our abort functions. So when I turn the key switch, the safety switch, we're going to make the launch ready. So what I expect to happen is that we're going to get an audible cue, a visual cue, a message on the message reader, and we're going to post the time on the countdown on the dashboard. So, and then when we abort out of that, by turning the key switch off or manually pressing the abort button, it should revert back to where we're at now. So if I execute this, our launch is now armed, so our rocket's armed and we're ready for launch. And we're notifying everybody visually and through our bell and audible tones in the background that a launch is imminent. But if I'm the safety officer at the range and I say, I see an unsafe condition or the rocket is not quite ready, I can abort the launch, which hopefully we get a notification down here that says, abort launch. And our cues are gone and our timer's reset on our dashboard. So that's our use case number 2. Next, we'll use our manual abort button on the console up here. So we'll go ahead and arm our rocket again. And now we will use our, that was bad. I think we lost power. Yep. So bear with me for a minute while we boot back up and restart the program, and then we'll go through the last little exercise here. But in the meantime, while that's restarting, are there any questions that you guys have so far, or is everybody kind of following along? Okay. Yes, sir.
So what analogies would you're familiar with ladder logic, right? That's traditional industrial automation where you have lots of inputs and outputs, maybe on factory equipment, assembly line equipment, and you have ladder logic that's on a screen, and you're tying inputs to outputs. It seems to me that that it's the same kind of thing that you're doing, but in, very event-driven,
Yes.
oriented. So I'm wondering, though, what kind of analogies, similarities, and differences there are between the two for those that are familiar with ladder logic.
So there was a question about how the similarities on the inputs and outputs relate to ladder logic, right? I'll do my best to answer that. I'm not sure how effective I can answer that question, but certainly all of the different inputs, and if you want to tie inputs to outputs or do very concrete actions, there's other functions in Py4j that can provide that functionality. We didn't talk about triggers today, but there's also a concept of triggers where you can intimately tie an input and an output together. Either they can be in synchronized state or they can be in a inverse state so that they're in direct opposite, or you can just simply invoke a triggered behavior on the output through the input, but without having to write a bunch of code. It's more like a binding expression, if you will, where you can bind this behavior to the input state change. Does that kind of get close to what you're asking? Okay. Any other questions? Okay, we're booted back up now. That's great. You can see our Raspberry Pi is booted up, so we're going to launch our program again. Now, this is JavaFX. We're sending the program from NetBeans over the network connection into the Raspberry Pi, and then it's going to load the JavaFX application. It does take a few minutes, or a minute or so, for it to load up. So I've launched it, and we're waiting for it now. But I have to admit, the new NetBeans. Historically, I've used Eclipse, and then I've moved on to, with the introduction of Android Studio, I've moved on to IntelliJ. But it's very refreshing that I can just come in here, execute my program directly from the NetBeans IDE, and then it just deploys the code, and I can do live debugging directly on the Raspberry Pi. That's been a very cool thing to have, and it makes it a lot easier to demo. Okay, well, there's a welcome sound, so now we'll just wait for the UI to load up. But our code's kind of running in the background. On the, you can see here on the console, make sure I don't power it down again. On the console, you can kind of see that we've initialized and our launch conditions are reset, and we're just waiting for the UI to load. Okay, so here we go. So we tested our use case 1 that we can't false launch. We've tested use case 2 that from the safety switch we can abort our launch scenario. I think we tested use case 3, or maybe that's when the power went down. So we'll do that again. So when we make our launch ready, we arm our rocket. Oops. I was in the opposite state. So when I'm going to go around this way so I don't accidentally trip over the power, but we're going to abort the launch again using this press button, and we have our launch aborted. So the final abort use case was we wanted these IR beam sensors to protect the launch pad, so if someone were to walk up there, it would automatically abort the launch. So we will run that use case now. So if someone were to break the beam, it automatically aborts the launch, resets our clock, and now we're in the ready state, non-ready state again. Okay, so I think we've done a good job of testing our different abort scenarios, so I think it's time to finally launch our rocket. Are we all good with that? So we will, for the last time, make ready. Our rocket's armed, and we will go ahead and launch our vehicle. So what's going to happen, it's going to start the launch activation sequence, which will start our countdown timer. Our launch has been activated, we're counting down, and ultimately we're going to launch our rocket. There we go, success. The demo gods have mostly been good. So that kind of just wraps all of the different topics that we've kind of talked about today using Py4j to create things and give us somewhat of a real-world demo of something we potentially could create. Let me switch back to the slides. So at this point, I'm happy to take questions. Just so you're aware, the slides are available if you want to download any of the sample code that we've gone through today or the slides that I have for the Py4j. They're available right now, savagehomeautomation.com/devox. And then these are the contact information and websites you can get access to, and Twitter handles for both me and the project. So at this point, if there's any questions or comments or fruit you want to throw, I'll take it all. Okay, well, with that, I will welcome Steve up to start his part of our show. And you want HDMI? Power.
No, wrong connector type. All right, and you guys get to see unstable 3D software crashes. First thing on the screen. Okay, so Jim showed you some excellent examples of how you can use the Raspberry Pi with Java ME technology to build, access a GPS, do all sorts of cool stuff. Robert has been launching rockets on stage, so that's going to be hard to top. But what I'm going to do is I'm going to show you some demos and examples of things you can do with the Raspberry Pi that you may not have thought about. So I have some cool examples today. Most of you might have a hat, but probably not one with a USB cable attached to it. So as you can see, this is a magical hat. We've also got a little robot here, which we will endeavor to make do cool stuff on stage. And then finally, I'm going to show you a little bit about this guy, my friend here. I want to give a big thanks to Michael Hoffer, and he'll be coming up on stage in just a little bit as well. So thank you for joining us, Michael, as our special guest. So first, we're gonna do a little driving test. In preparation for DevOps, I was doing lots of hard work and coding and preparation, and part of the rigorous preparation for this particular talk involved something which was very challenging for me. I had to practice some of my driving skills, work on my reflexes. Anybody a Mario Kart fan? Mario Kart 8? So I play this with my daughter a lot, and this particular game, this is for kids. Very easy, lots of unlockable achievements. If you fall off, they just dump you back on the racetrack, and you just catch right up with guys. This is kid stuff, but a real gaming console, the old NES. This is where pro gamers came from, and even the old Mario Kart was very unforgiving. So if you remember Rainbow Road, you would you fall a little bit off the track and forget it. On 200cc, you've lost the race entirely once you fall off. No chance. Anybody an old school gamer like Ninja Gaiden? Yeah, this game is impossible to beat. You die and that's it. You're game over, start over again. And it looks cute, but the next game here, Mega Man, is not cute at all. Mega Man 1, the rest of the series, was easier, but Mega Man 1, the controls were horrific. Trying to jump and shoot at the same time and catch those little guys who could hide in their shells was physically impossible. So those guys looked cute, but they were quite evil, and shooting games as well, just incredible reflexes. So I was working hard in preparation for DevOps, doing what any good geek does. And I came to enlightenment. I think I've reached a level of video game enlightenment that all of you will appreciate. Anyone know what this code is? What's this? The Konami code. Oh, okay. We got a real video game geek here. Okay, so I'm going to challenge you. Come on. Oh, and let me give you. Is it okay if I give him the mic? All right, here you go. So in preparation for this, I built us a little race car that we can compete with. This, of course, is built using Raspberry Pi technology, and we're gonna endeavor to drive them around on stage and see how much physical damage we can do. So I got a nice little racetrack here too that we're going to use to race. And let's see, we need a little checkered green flag for our start place. Okay, so the way this guy works is I got a little infrared remote for you to try out. There's an infrared receiver here on top that communicates over serial. And we're going to see how your reflexes are. So if you want, you can hand me the microphone so you get better control. And we'll do, what should we do? Like a proper 3-lap race? Race around the track 3 laps and see who can get a better time?
Sure.
All right, excellent. Now, I'm going to give you a chance first to get a little comfortable with the controls of the guy here. But the way this remote works is the center button, play, goes forward. And if you click it again, it will stop him. So you can just press that, point at the IO remote on top of him. Yeah. And then you can go left with that button. Yeah. Right. Very good. Okay. So you're an expert. Point at him to get a better connection. Yeah. So, right, easy. You can just go around the track. If you get stuck and you want to go backwards, there's even a reverse switch. Just press that top right one. There you go. Backwards, forwards. Yeah, so easy. You got it?
Yep, got it.
All right, so who wants to be our timer in the front of the audience? Here, tell him to stop. Tell him to stop turning. He still thinks he should turn. All right. So we got an official timer. And what I want you to do is, as he's going around, give us a lap time for each lap, and let's see how he's progressing. So, and tell him when he's ready to get started. All right, and feel free to chase him a little bit if he gets too far away from you. So that's pretty good. That's pretty. I think you passed the driving test so far. Very good skills. You gonna make that sharp corner? Oh. All right, so we're almost ready for the first lap time. Oh. So you're trying to give me a little handicap here, right? Yeah. All right, what do we got? 55 seconds. 55 seconds. All right, let's see. I bet your second lap will be faster than the first. Oh, almost there. So this corner got you last time, this sharp corner here. You think you can handle it? I think that counts. Your wheel stayed on the whole time. All right, what do we got? 41. Oh, 41. Oh, that's a good lap time. You're in the home stretch. That's good. You're playing fair. So you guys know that I'm not going to play fair, right?
Almost there.
Oh, finish, and 51. All right, so I think, what is his combined score? Give him a round of applause. All right, so don't go too far away. And so when you're ready, give me a good start time, and we'll see how I do.
Ready?
Yep.
So 3, 2, 1, go.
Oh.
Disqualified.
Disqualified already. Wow, you're a tough partner. You're a tough person to play against. See, now I'm not going to fall off the track like you did. This is my months of practicing video games. Very careful attention to detail. You know, you fall off the track on Rainbow Road, you don't get any second chances, right? Oh. No, I think I got that corner. All right, let's try behind my head. How'd I do on my first lap? 45. Okay, so you still got a better lap time than me. So I think I need to increase my cheat level, right? All right, let's see how I can do. So you have to like concentrate more, and he gets faster.
Did you program this in?
All right, 27 on my second lap, and at this point, I think I'm going to need some assistance here. Can you give me a hand? All right, that was good. Now I'm completely. And the tire tread came off too. Wow, that was a good one. Okay. So I think I'm disqualified by having a broken car. So we have a winner. Congratulations. All right, thank you very much.
Thanks, Steve.
So as you guys notice, this is not your average little car here. This is actually a Java-powered car, and he's a line follower. So he actually knows how to follow the line and do the right thing most times, except when his tire treads come off. Like that. And you execute the kill switch, kind of like Robert's kill switch, except it's a little bit less noisy. So our buddy here, I like to call him Mr. Grabby. He looks like a crab, and he has a little claw on the front. And he's actually built using an aluminum shell, so it's fairly rugged. This guy's fallen off the stage a couple times, taken a beating, still came back for more. And he's controlled by a Raspberry Pi. So on the top there, you can see there's a Arduino shield. This connects to all the motors in different devices using RJ25 cables. It uses a cooking hack shield below that to hook up to the Raspberry Pi. And then below that, we have a Raspberry Pi, which is running Pi4j to do all the communication over GPIO pins. So that controls the motors. It controls the remote control using serial, so that's using UART. And it also, the motors are pulse width modulation, so that's how you control the speed. Noticed at the beginning he was going about half speed, and then I increased his speed, cheating slightly on the last couple laps. So the way pulse width modulation works is you can adjust the power given to the motor by turning it on and off, and it does two things. One is it reduces the actual power to the motor, so it uses less energy since you're pulsing it on and off, but it also allows you to control the speed as well fairly reliably. So you can use this to speed up or slow down the motor. And the last thing which I had in there was the actual line follower itself, and that's what picks up on the nice surface here to follow the line. So you can see the line follower there, the image, and it's facing the ground, and it looks for the white and black line here I've taped on the floor. And when it goes off the left or right edge, it'll reliably follow it. There's also some batteries, motors, and other stuff you can see on the underside of our buddy Mr. Grabby. So a little bit about how line followers work. So this particular line follower uses an infrared transmitter and receiver, which bounces off the white and black surface. And you notice it has two pairs of them, a left and right sensor. So what happens is if it goes off the right edge, it will, we want to steer to the left to get back to the line. If you go off the left edge, you see white, you want to steer to the right to get back to the line as well. And if we see two black lines, then we know that we're on the line. If it's two white lines, well, we're somewhere really bad. We don't really know what to do. So I think the algorithm just kind of ignores that. But with two sensors, you can kind of more easily follow a line. If you had a single line sensor when you went off, it'd be harder to tell whether you were off on the left or the right edge. So this makes it much easier to chase the line and go fairly quickly. And here's a little bit about the code for our buddy. So basically, I'm using the same sort of code Robert was showing to access the two pins using Pie4J. It turns out they're on pins GPIO 13 and 14. Probably the trickiest part of this particular project, if you wanted to do it yourself, is figuring out the pin mapping from Raspberry Pi GPIO pins to the Cooking Hack Shield, which does some swizzling of different GPIO pins to the Arduino Shield, and then figuring out which of those Arduino Shield pins goes to the actual physical motors and devices. But they have schematics for the Make Block Shield, wonderful wiring diagrams. They have schematics for the Cooking Hack Shield, and code for both of them as well if you want to read some C libraries. And then you can reverse engineer exactly which pin it is if you're careful, or just do it by testing as well. You could use a multimeter. So it checks the state of those two. It comes across as digital high or low for the left and right line follower. And then you, based upon whether you're lost on the left side or you're lost on the right side, you know which way you should run. So fairly straightforward, and something most of you could probably put together with this. So you'd need a Make Blocks kit. This kind of think of it like Legos for big kids. They give nice aluminum milled pieces with screws, and they're riveted in a way where you can attach screws at any point along any of the rods, so you can do fairly complex structures. The early version comes with the ME-based shield, so if you get the later versions, it has a built-in Arduino, which you'd rather get the one which has the base shield instead. Then a Cooking Hack Shield to hook up to your Raspberry Pi, a 1-amp battery, which is what I'm powering the Raspberry Pi off of, and I put all the code online as well, so you can check out the code on my GitHub repo to give it a shot for yourself. Okay, so a little bit of, you guys are all expert drivers now. You've learned the secrets of my driving practice, but we're gonna see how good you guys are at magic. So anyone here a magician? No? Anyone been practicing their magical skills? So I have a magic hat here, and this is how you know I'm a magician. Voila! Now I'm a magician. And for our first magic trick, we're gonna need some volunteers from the audience. So who feels like being our our guinea pigs for the show tonight? Just raise your hand, and I'll call you up to the front. Who'd like to give this a try?
We've got one here.
Oh, okay. Come on up. Sorry for the bright lights in my face. I saw someone in the back right, maybe stretching. Yeah, come on up. Okay, yeah. 3, and let's get a 4th person up. Sorry about the lights in my eyes. Okay, one of our... Oh, okay, in the back. Come on up. All right, so I'm going to need the audience's help for my magic trick as well, because my magical powers have been waning. So I need all the help I can get. So what I'd like you guys to do is this is perfect. Just line up. And okay, we're going to nominate one of you to be the card shuffler. So we've got a normal deck of cards here.
You want me to shuffle? Yeah.
So yeah, just step up front here. You're going to be our card shuffler, passer outer, and make sure those are nicely shuffled. Give me one of the cards, just for verification purposes. Yeah. Okay. So just look over and make sure that I didn't play with the deck or do anything tricky with the cards. Looks like a normal run-of-the-mill card. Nothing special, right?
Quite slippery.
Yeah, the cards are a little bit slippery. It's a new deck of cards, so to be expected.
Okay, I've got them.
You got it ready? All right. Let's make sure we get all our cards in the deck. Okay, so what I want you to do is, all right, so you three, get moving closer. Come on up with me.
Okay.
Yeah. All right, so what you're gonna do is, we're not gonna trust me in this because I might try to game this.
Yeah.
So pick a card out of the deck, any card, just randomly.
Yeah.
Yeah. Okay. So I don't touch it. Put it in the hat. Drop it in the hat. Okay, and we're gonna give you a card. Grab the card. Yeah. Okay. Don't show anyone. All right. Second card. Yeah.
Yeah.
Okay. Here's your card. Is my dandruff that bad?
I don't know.
All right, so you guys all have an anonymous card, and let's see if I can practice my mind reading skills. But I can need a little help from the audience too, so you guys have to help me out with this. All right, so I'm thinking one of you guys has a heart. Okay, so you're giving me the stone cold look, and you were fidgety, but you were perfectly relaxed. What do you think? A little too relaxed. Wait. So, was somebody cheating? Did you see his card before? Okay, no. This is a professional magic show. We won't have any of that cheating here. But you have a King of Hearts? Oh, all right. One down. All right. So does anyone in the audience have like a favorite number? All right. I heard somebody say 5.
A lot of people said 5.
A lot of people said 5. Yeah, but What's your favorite suite?
Maybe club.
Club? Yeah, okay. How about 5 of club? Oh, okay, 2 down. And we got one more guy left. Now I'm gonna need your help with this.
Okay.
Yeah. So what do you think? I heard a lot of 6s.
6?
I heard a lot of 6s in the audience. You think 6? Or
Yeah,
7? There was one guy saying 7. Should we go with 7 or 6?
One guy 7 and some guy. Go for the 7.
Go for the 7? Okay, we'll go for the 7. And maybe, I don't know. Spade? 7 spade?
Nope.
Oh. All right, well, we'll go with the 6. 6 of spade?
Yes.
All right, so all 3 of you, thank you. All 4 of you, thank you very much. Give these guys a round of applause for being great volunteers. Okay, so as you probably guessed, this game was slightly rigged. My little magical hat. Most hats probably do not have lights inside of them and USB cables attached to them. And if we actually go back and look at a picture of my magic hat, they also probably don't have NFC and RFID sensors in it as well. So what I was using is, it's actually quite common if you ever watch poker games on TV, or if you have electronic poker tables, to use cards with RFID chips in them. So these have the MeFair ultralight RFID cards embedded inside of them. And even if you hold them up to the light, it's really, really hard to tell that these are RFID-based cards. So what I'm going to do is I'm going to put you guys on the honor. There's 52 of these cards. Hopefully, I'll get 52 back at the end. Here, pass them around. But they're really hard to distinguish from normal playing cards. And what I have here is a sensor built into the hat where every time he dropped in the hat, as you saw, it would show up on screen with exactly what card was displayed. The code here in NetBeans I was using, and I was doing this via remote deployment to the hat, which has a Wi-Fi connector in it as well. And one of the questions, actually, somebody passed one of the cards back to the front, so I can just demo this early. One of the questions I got on break was, how good is the NetBeans integration? And it's really easy to set up. So all you need to do to set up the integration with your platform is you create a new remote module and then give it the username and password on your Pi and the IP address. But the person came up to me and asked me if it supports remote debugging, which I'd never tried before. So we gave it a try during the break, and I'm going to show you the results. So here's our IoT hat code. We'll put a little debug right here. Boop, boop, ba-doo. Let's grab one here as well. There we go. Okay, so it should, when it gets to that line to read the card number, it should pause for us in the debugger. And I'm going to execute the same application again on the hat that you guys saw before, and this is going to read the RFID card and then show on the terminal, on the output, exactly what happens. And you can see it's pulling up the debugger now for the remote run. Okay, there's a debugger. And it says, unknown host exception. Oh, wah, wah. Where's our hat? Come on, Mr. Hat. Run, run. Oh, and we're actually already running. That might be a problem as well. So, one more time to see if we can chat with our hat. Okay, so you can see it's kicking up the debugger. Here's the output where it's actually executing the command line. And you notice this time, the output actually had the debugging flags on there as well. So it has -x debug, and it kicks up a port. And then we have our debugger console, and when we flash the card over this, so we have a breakpoint in our code, and we can expect the variables on our Raspberry Pi. So this is a great example of using the NetBeans integration, directly running on your wearable hat, and then being able to do remote debugging as well, right on the fly. Okay, so a little bit about our hat. Here's an enlarged picture. What I'm using in the hat is actually not a Raspberry Pi. It's a Raspberry Pi clone called the Odroid W. The nice thing about this is it has exactly the same pinouts as the Raspberry Pi, so you can hook up the same GPIO ports and wiring. The spacing is exactly the same as well in the headers. It uses the same Broadcom chip as the Raspberry Pi does, but the size of the board is about half the size of a normal Raspberry Pi, so it's really tiny in comparison. A single USB port, which I'm using for the Wi-Fi adapter, and it also has built-in circuits on the board for power charging. So there's a little battery on the top left side there. That's what's powering the Pi hat. And it will charge that whenever it's plugged into USB, and also allows you to run it wirelessly. So I'm going to pass the hat around as well for you guys to take a look at. It's partially open. If you just kind of peel the fabric back a little bit there, you can see the internals of the wearable hat. And then at the top right there, you can see the RFID sensor, which has how it's actually picking up the cards. It'll work on either side. You can drop cards in the hat, or you can flash them across the back of the hat as well. And if you're interested to use RFID card readers, one of the things I discovered while creating this project was that it's not the most well-documented API in the world to use it on the Raspberry Pi. So there's some good existing articles to explain how to use USB card readers, but specifically using I2C, SPI, or UART with your card reader is not as easy as you might expect. The chip I'm using is a PN532 chip from Adafruit. So you can readily buy these from Adafruit Electronics. There's a bunch of other providers which have breakout boards that use the same PN532 chipset. It's also the same chipset that's in a lot of the Android phones and other devices. So it's compatible with a wide range of different cards. But to access the chip directly, you have to use a library like libNFC. So I'm using that to talk directly to the chip. And I tried all three interfaces, I2C, SPI, and UART. Apparently there's a bug on a bunch of the chips where I2C support doesn't work. The address fluctuates randomly. So on my particular RFID card, SPI and UART were the only available interfaces. I2C was buggy. Although your mileage may vary, I2C is supposed to work on these boards. So I think that was just a bug on a certain number of them which came out. And then you use libNFC to actually set up communication to the chip. You can use NFC PAL and NFC list to get the devices and PAL the devices. But to expose it to Java, libNFC is not enough. You need to get a PCSC interface where Java can use the Smart Code IO library. If you're using a USB reader, PCSC automatically hooks up to USB card readers with proprietary drivers, but if you're doing a real embedded project, you'd probably rather not use a USB interface. So there's a nice bridge between libNFC and PCSC called IFD-NFC, which makes your libNFC device look like a PCSC device to the PCSC daemon. Okay, so anyway, long story made short, get libNFC, get PCSC, get IDF-NFC, or check my blog post coming out shortly, which explains fully how to set all this stuff up. And you can create your own little wearable hat with an RFID card reader inside of it. And then here is the sample code using the Smart IO library to access the hat. So this gets you your terminal factory and your card terminal. Here's the code which waits for the card. So this goes in a loop and checks if the card's present, handles the card, and then goes back and waits for the card to disappear and goes back and forth in a loop. And then finally, reading data off the card. So this connects to the card, gets the data off of it, and then I use this to determine which card is read. It turns out that I couldn't find a pattern to the playing cards, so what I did in the code instead, and if anyone's smarter than me and can figure out a pattern, I'm welcome to improvements on this. But right now, I simply have a mapping from the hexadecimal tag ID of the card to which card and suite it is. And there's 52 entries in this property file, and it simply does a lookup in the property file for the appropriate card. Okay, so we've shown a couple demos of a car, of a smart hat, which is somewhere in the room, but I'd like to invite my, my friend, Michael Hofer, to talk a little bit about the Ultimaker. Okay, and because we want our Ultimaker to be happy and working, while he's coming up here, I'm gonna... Oh, there you can see my blog entry in progress. I'll eventually hit the publish button, but lots of things to do. Okay, now we're hooked up to the Ultimaker, and should I push my luck here? and run it from Octoprint? Why not? All right.
Yeah, try.
Give it a try. Oh, and you have a microphone as well. Here you go.
Okay.
Okay, so this is going to kick off wirelessly, communicate with the printer, and then kick off a print job. But while it's kicking up, let's chat a little bit about the Ultimaker 2, and then we'll talk about the software which you've written, and then go into some details on different projects and things you can print. So let's see. You want me to talk about the Ultimaker first, and then you'll do the software?
Yeah, actually, the Ultimaker is a nice printer if you want to get started with 3D printing at home. So I bought the do-it-yourself kit from Ultimaker. So I went to a conference on 3D printing and talked to them. And yeah, I think it's really nice technology. It's FDM-based 3D printing. So you just melt plastic inside the printing head, and then you add one layer on top of another. So many of you might have seen that already. If not, we are in the playground area and have some amazing pieces that we printed that take several hours to print. So come by if you're interested. Yeah.
Yeah. So this is a great big kid toy. So tell your boss you have an extremely important project that you need it for.
Yeah, that's what I did. So that's why I have a printer in my office.
But the way this relates to all the embedded stuff we're doing is it's also a great platform for prototyping different designs for embedded development boards. So Michael was mentioning the Ultimaker 1, which is, you have cool stuff with you. Michael was mentioning the Ultimaker 1, which is the first generation of the printer. This is the Ultimaker 2, so that it's a little bit more convenient since it comes in a packaged solution already assembled. But it still requires quite a bit of blood and sweat to keep it running and maintenance and all that stuff. So this is definitely early generation. Just think about the early inkjet days when you had very unreliable inkjets which constantly got jammed and clogged. And
exactly, and also from the price range, it's kind of similar. I mean, you could easily spend €1,000 for an early inkjet printer, which didn't work that well actually. But yeah, I think the Ultimaker 2 is quite amazing. And also, when I was at this conference, then the Ultimaker guys, they were actually able to print something that I created, and they were spontaneous, and they trusted their technology, and that's why I just like that.
Yeah, one of the other nice things about the Ultimaker, we use MakerButs and Affinia printers and a whole bunch of different types of printers in the Oracle demo team. This one is the only one which has an open source design, so you can actually get the model files and the source code and everything for the printer itself, which makes it much easier to troubleshoot and do enhancements. A bunch of the parts of the printer up here have actually been printed on the printer itself, so it's self-augmenting itself over time and getting better and better. So this is one of the items which we printed recently in the Ultimaker. It's a Raspberry Pi Model B case. I think this is actually the B plus?
I think it's the B plus case, right? Because you tried both, I think.
And it's a good example of printing something on the printer which is practical. So this is a good start. It was actually defined using Java geometries, and you can combine this with other things. So one of the things Michael did is he turned this into a little car by adding on wheels and spools and different things to spindles and things to.
That's true. So I created a project called Pi on Wheels, and it contains a small IDE that lets you talk to the Raspberry Pi, and also lets you create the geometries actually, so you can actually change the robot itself, like giving it bigger wheels and stuff like that. And and that's the board was just the first part that I created for that.
Yeah. So if the cameraman can get a little view of the printer, and if you wouldn't mind switching to the camera on screen. It's actually top left. Okay. So you can see that the printer is actually starting a print. The very first thing it does, if you noticed, is it poops out some plastic in the corner. And this model is going to print a bracelet. So I've sized it for large European hands. It's a dynamic model where you can actually adjust the parameters on the fly. And let me show you both the printer console that's going right now. So we have this printer, like a good IoT talk, the printer is wireless. So we're hooked up to it remotely via Octopi. And Octopi is running on our Raspberry Pi on the side of the printer. So this allows us to remotely control the printer via USB. And you can see the blue line is the heated bed. So that's the temperature of the bed, the build platform. The red line is the nozzle temperature. So the nozzle, we're printing PLA plastic, which is a corn-based plastic, and that wants to be printed at about 210 to 230 degrees. Faster or slower depending upon how quickly you're printing, and how much flow you want to get out of the print head.
Yeah, the interesting thing also is that the printer actually can print quite complicated stuff, like the one I brought here.
You wanna hold that up?
Yeah. This is very complex geometry that you can create in Java code with the library I created called JCSG. So it has very few basic operations, and then you can parameterize the geometry. And yeah, it's completely open source. And I also integrated that into my visual programming environment called VRL Studio. So you can just check it online and download that. And this piece, I mean, it's very complex and hard to make with other technology because there are parts that are hidden inside other parts, actually. So yeah, that's just what fascinates me, that you can really even print moving parts. We also printed gear mechanisms on the Ultimaker, even with PLA. And also something that I try to do is to print parts for an actual drone. So there the kind of idea was to take a bird's bone and then try to reassemble that geometry with a lot of air in it, but still stable geometry, and then just having a code generator that creates the arms for the drone and everything else, except for the blades, of course. And then, yeah, this is also part of the library. And if you try to build your own drone, this is even cheaper buying a printer and building your own drone than buying a drone, because usually it breaks when you practice it, and then you can just reprint stuff. So that's very cool.
Okay, so what I put up on screen is the output from the Pi camera. So we've got a little Pi camera mounted in the top left corner of the printer as well. This is hooked up via Octopi, and it both gives you remote access to see how your printer's doing, so you can take a look at your printer and do manipulation of the temperature or other printer parameters, but it also is capturing a time-lapse video of the print process. So when the print finishes, we'll have a little movie which will show us the entire print stages from beginning to end, showing a print in progress. Just to give you guys an example of that, let me grab a random one here, something which doesn't say failed. Okay, so we're downloading one of the movies from the Raspberry Pi, and this will show up in the movie player. Oh, there we go. He popped open. And should give us a nice example of a print from start to end in time lapse. And you can see over time it's building layer by layer. One of the other nice things, since it's integrated with the printer, is it can actually do single layer time lapses. So since it knows each of the moves of the Z layer on the printer, it can capture exactly one photo per each Z layer as well. Okay, and then while we're here, let's show some of your software as well, Michael.
Yep.
Let's see. JFX SCAD. So, we have a running theme here of embedded stuff and JavaFX enabled UIs, and this is a really cool example of running JavaFX to show visualizations of what we're going to print on the 3D printer. So this example is a very, very simple cube with a sphere taken away from it. And you can see the code on the left here where it creates a new cube, gives it the dimensions, creates a new sphere inside of it, and then you get the resulting shape by subtracting the two. If we instead, what's the add thing? Is it just add?
Yep. So no, it's union.
Union. Okay, thanks, Michael.
Union. So
that's why he's here. Okay, so that guy is a union instead, and then we can change the sphere, make him slightly smaller, or much bigger. And then if he's large enough, he'll actually override the outer box, and you won't see that anymore.
Yeah, and then you could also do other operations like intersection, which is quite interesting, because
I'll get it.
yeah, just to
Intersect or intersection?
intersection, I think.
You think?
No, intersect then.
Intersect.
Okay, sorry.
One of the two.
This is actually Groovy code, so we use the Groovy shell for that. So if you stop typing, it automatically compiles and runs the script. And here you see that it just takes the intersection of the sphere and the cube. And also the software comes with samples for the robot. So if you go to the sample menu, you can, the board mount for the Raspberry Pi that we already saw. And if you know Thingiverse, which is a really good web page for getting 3D models, we also published it there, so you can download the version for Raspberry Pi B and B+, and also, of course, the source code itself. And the cool thing about the software is that it's completely parameterized, and something to change something like the bracelet, for example, is very, very easy, because you basically have only cylinders in that case, and you just remove other cylinders from that. And then, like here, this is the shape, actually. And also we did an intersection between the cylinder and a sphere, so it has a slightly rounded outer shape. And so this is a method for defining geometries that is used in commercial programs as well, and also some other projects like OpenSCAD, for example, but I wanted to have that on Java, so I wrote my own library. And also when you use it as a library and not as a program, you can actually just ask it to give you a JavaFX node that contains a 3D node already. So it's really incredibly easy to integrate a 3D visualization of the stuff you're going to print.
All right, so while you've been chatting, I'm gonna dump this out and open it in Cura. So Cura is software for doing slicing. So first you need to create a 3D model using something like this Java constructive geometry library or JavaFX SCAD. And then you take the STL file and you import it into Cura, which turns it into instructions for the printer to actually do a print. And then thanks for crashing. I just popped that guy, which is our new model, into Cura. Now, that doesn't look much like a bracelet currently, but what we're going to do is rather than printing the whole structure, we're going to print it with 0 fill density. So normally if you print objects, you want them to have a top and layer thickness of some thickness and then have an infill to fill the center. But as you can see, when you do that, what you're going to end up with is you're going to end up with a solid object, which is completely filled on the center. So you see the bottom has a solid layer, and then we have the infill, and then the top is also closed. But if we change this to 0 for the bottom and top thickness and 0 for the infill, then what you get instead is you only get the outer walls of the shape, and this gives you a nice bracelet that you can hopefully fit on your wrists. And we kind of customize this on the fly. So I added, rather than 22 spokes on the outside, it has 24, so it's slightly larger. I also increased the height a little bit, so you can see it has more of a curve to it, and it's taller than the one which we're printing out here.
Yeah. And a few things about the library. It's actually, I try to optimize it for use with NetBeans or Eclipse with autocompletion. So it's a Fluent API also, where you can add transformations to it and just modify objects very quickly. And it works in Java and Groovy, as I already mentioned. And the license, I didn't talk about the license, but it's BSD, so you can literally do anything you like with it. And what I think is really where the potential is, if you have some projects like the Pi on Wheels or the Mr. Grabby kind of robots, then you could actually ship with a software that prints the robot itself and lets users change the parts for the robot and customize it.
Sorry, my computer is going absolutely bat crazy right now.
Okay.
We're going to see if we can get PowerPoint back up, hopefully. Okay. So here is the information about the JCSG project and the JFX SCAD project. You can find both of them on GitHub. And what I was showing was just the current poll from JFX SCAD, which I pulled down this morning because you told me it had new features.
Yeah, correctly.
So I grabbed that, and it was really cool, much better.
And actually, we have talk about 3D printing and teaching Java and also visual programming on Thursday evening. So if you want to know more about that, you can also come to the talk. And there we also will talk about the visual programming environment that I develop at university. So, and we integrated these projects to that.
And here's a quick example of another 3D print being built up. So this was a clear bracelet, which we built. And in closing, I actually have a little announcement. So I want to thank Michael very much. Give him a big round of applause. And if my co-speaker, Jim, and why don't you come back up, Robert, as well? Here you go, Jim. So, for the first time at any conference or event, or I think probably anywhere in the world, you guys are privy to the new announcement. Jim Weaver and I are going to be co-authoring a new book. So we wrote the Pro Java FX platform book together several years ago, and that was a lot of fun. And I'm very pleased to be working with Jim again on a new project. We're going to be authoring Raspberry Pi with Java. It'll be a McGraw-Hill title. Do you remember what our subtitle was, Jim, offhand? It had IoT in it. I remember that. All right, I'm putting you on the spot. But it's going to be out. The planned release date is for Java 1 next year. We'll have a print copy available. And it's going to cover doing different embedded projects with Java SE Embedded, Java ME Embedded, and be a good reference platform with a project-based approach for getting started with these technologies. So I hope you guys look forward to it. And our blogs will also have quite a lot of information on it. So you can check my blog, steveonjava.com. Jim Weaver's blog is JavaFX Expert.
JavaFXpert.com.
Yes. And Robert, do you have an appropriate?
Blog site, savagehomeautomation.com, or the project site, pi4j.com.
Cool. So thank you guys very much for attending our Java with Raspberry Pi talk, and we hope that you've learned a little bit today that you can take advantage of in your embedded projects.
Thank you.
Thank you.